So my name is John DesJardins, and I work for Hazelcast. I'm actually CTO for North America for Hazelcast, and also VP of Solution Architects globally. I've been with Hazelcast since last August, and before that I was at Cloudera for a number of years, and before that I was at a company called Software AG that a lot of people haven't heard of, but you may have heard of some of the different products that we had, Terracotta, Web Methods, Apama, Stream Processing. I've been working with distributed high-performance computing technologies, for more than 10 years, and I'm excited about talking to you today about machine learning and why stream processing is an important component of real-time machine learning, and talk about some ways that you can achieve kind of operationalizing machine learning using Java framework that Hazelcast provides, and give a little bit of a demo of that. So before I get started, I'm just curious, sort of how many people here have been playing around with machine learning at all? A little bit, okay. And how many people, I guess most of you are also Java developers, or a lot, at least some of you, okay. Good. The reason for coming to Hazelcast for me was that at Cloudera there was always a struggle from working on training a machine learning model, preparing a lot of data, and then figuring out how do you actually make that operational. How do you run the model within some kind of an application architecture? So data scientists spend a lot of time playing with data, exploring the data. They get the right data, or they think it's the right data, and then they want to somehow turn that into some kind of an application. And in the meantime, in the industry, we see that AI is driving more and more disruptive applications. So there's a more and more demand for this AI capability, while at the same time there's this disconnect between the machine learning world and the operational or application world. And that drive for more AI creates challenges, and I just want to talk about how we can address some of those challenges. To give a little bit of a background, Hazelcast is the platform that I'm going to be talking about today, what really drew me to this company was the ability to actually have a lot of capabilities similar to what we had at Cloudera with Apache Spark, but in a platform that's more Java friendly. Did you have a question? Oh, okay. Being able to have a Java-friendly solution that would allow you to distribute and execute logic, as well as to do the preparation of the data. The unique aspect of Hazelcast is that the in-memory compute platform, which is very similar to Apache Spark, is actually built on top of an in-memory data grid. And why that's kind of relevant is that traditional solutions like Spark or even Flink or various other solutions, they are complex in how they distribute computational logic, how they orchestrate working with data, and so they become very difficult to manage, and also very difficult for Java developers to use. The IMDG platform really was built on simple APIs. So hash map is a very basic construct that is an example of a simple API that by extending it and allowing it to distribute that API and run it on a grid architecture, suddenly that simple API becomes very powerful. And really what we've done is done the same thing in the in-memory compute space with the ability to actually take simple APIs like Java Streams or like Java's Executor Service API and run them on top of the data grid. But at the same time, because we're running in a integrated platform, the data and the compute, the platform's aware of the data architecture and where data sits in different partitions on the cluster. And so you can have a data-aware approach to executing the computational logic. So, you know, the simple value proposition of JET is that it's based on a simple jar file that is integrated with the data grid and the stream processing. And that simple jar file can be run in a distributed cluster of Java applications. So if you think about Apache Spark, you've got to have Yarn, you've got to have Zookeeper. If you want to do data lineage with Cloudera, you need to have the Hive metadata store and Cloudera Navigator, Cloudera Manager. I think there's at least 2 other components that I'm forgetting that you have to run in order to run Cloudera Spark to be able to do distributed compute. So what people tend to do is they tend to just say, well, let's just run it in the cloud, which is great for batch compute, but not so good for taking something and integrating it into an application. On the other hand, Java, you know, is what a lot of applications are already written in, and so having something which is based on just one Java runtime that's distributed in a cluster, that's actually pretty easy to integrate into a Java application architecture. And it's pretty easy to go to an operations team and say, hey, we've got a new Java application. It's going to be doing something called stream processing and machine learning. But basically, it's just a bunch of Java applications or Java servers. So that also makes it very cloud-friendly and easy to operate. So why does that matter for stream processing? Well, you know, first of all, Cloudera definitely innovated with stream processing along with Databricks and the others who came and brought Spark to market by figuring out distributed compute that was near real time. And before that point in time, there was something called Apama. There was another product from TIBCO called Business Events, another product called Streambase, that were complex event processing. And so complex event processing products, welcome, were able to do real-time stream processing or analyzing data in motion, but they weren't highly available, they weren't distributed, and actually they were very complex and proprietary to manage. And so, Spark came along and said, let's come up with a simpler open source approach to distributed stream processing based on concepts that originated with MapReduce and Hadoop, but taking it and making it more suitable for real time, as well as able to represent more complex models using something called directed acyclic graph. And of course, when you're trying to represent a lot of complex data flows, being able to represent a more complicated computational logic is critical. At the same time, the DAG also allows you to distribute the work on a cluster of computers more effectively. And so that was really a breakthrough. But because it was still micro-batch, and because it had a complex runtime for how it would orchestrate the execution of the DAG, it was still, had a lot of room for improvement. So the third generation, and the reason I came to Hazelcast is because Jet and Flink had come out and really improved upon Spark by simplifying it and making execution in a directed acyclic graph that was more real time and lighter weight. The difference is, I believe that JET actually really takes that even a step further by building a stream processing DAG-based technology that's built on top of a data grid. So, why does that matter? It matters because there's a lot of applications where, when you're trying to integrate things into user experience or into other real-time interactions, it needs to happen at very low latency, right? If somebody's clicking on a website and you're going to analyze that in real time and then change the behavior of a website, latency, even a little bit of latency, is just not going to really make that a very good experience. So when you get into very high throughputs, we can see that the benchmarks show how much faster JET is than Flink and Spark and other frameworks. So, fundamentally, lightweight and low latency is kind of a breakthrough that we're bringing to the market. And so why does this matter for for machine learning? It's because when you're trying to operationalize your machine learning, you're trying to look at a lot of data in motion, and you need to do a lot of preparation of that data to be able to bring it to your algorithms. And so an example could be, personalization in online retail or online media sites, or, personalization with machine learning to kind of detect propensity to abandon a shopping cart. If I'm going to abandon a shopping cart, it's probably because I've got multiple shopping sites open and I'm actually comparing prices, and so you can actually analyze my web clicks using a machine learning model and start to see anomalies in the interaction, the patterns, and actually start to look for some kind of a flag that would indicate this person is likely to abandon the cart. You don't want to make an offer to everybody, because that's just giving money away. So the key with cart abandonment is to, in real time, identify that small percentage of people who are about to abandon the cart, and then at the right time intercede and give them an offer. So probably should walk through a little bit more. So your e-commerce servers need to talk to something that can store a lot of data about the customer. So there's contextual data, and having that contextual data in a data grid where you're writing through to the database means that at low latency that data can be retrieved, both to improve the response time of your application, but also to feed into a cluster that will start to prepare that data and combine it with data in motion that will allow you to then have an appropriate set of data to feed into your machine learning model. So at the same time, there's a lot of new techniques that are coming out in the machine learning world. And so, the different types of algorithms are constantly improving. That whole world is one that really requires an entire separate specialization of knowledge. If I want to learn about convolutional neural networks, because I'm going to be doing image processing, or I'm going to be doing other types of advanced analysis that want to leverage that multi-layered neural network that can categorize and predict and drive sophisticated AI capabilities, you're going to need specialists who can do that. And those specialists are going to need to be able to work with data, prepare the data, try out different data sets. Those guys don't know about Java applications, and most of them don't really want to know about Java applications. So they're writing things in Python, and they're not really thinking about the other side of the equation. So how do we kind of bring these worlds together? So if we look at the data flows, you'll see that there's always going to be kind of an ETL processing that's more offline, where the data scientists and data engineers are trying to pull a lot of different sources together to try and understand, what is the pattern, what is the raw data that I can feed into an algorithm, and then look for patterns, look for different things. So, there's often a need to take raw data and do some feature engineering where we identify, for example, categorize images, or we might categorize web clicks into different types of behavior that we want to then be able to draw some insights. So there's a need for, during the raw data, there's a need to sometimes do some supervised and unsupervised learning, look at features, identify buckets, and then say, okay, for this bit of audio, this is a language, this person's saying something, or this person's, there could be sentiment. Sometimes you have to take that raw data, categorize it, and then have people look at it. So for example, Google and Facebook, they've got just teams of people who get output of classifiers, and then they just kind of go, yes, that's a dog, or that's whatever. This video is an interesting piece of a football match, or isn't an interesting piece of a football match, and then training that data and identifying the features. They can be labeled, and then now we have useful information for the machine learning to create a more sophisticated algorithm. All of that's happening in batch, but we have to then be able to repeat that in real time. That requires a different set of challenges. In addition, we not only have to be able to repeat all the same steps in real time, it's important the sequence of, first engineering the feature, categorizing and classifying, and then, applying other algorithms and techniques at the end to either determine whether we want to make a prediction or whether we want to just, trigger a certain action. And all of that has to be distributed and scalable. And that's where a directed acyclic graph comes into play, is the fact that we can represent computational logic in a consistent flow, so that if we've executed this computation in a distributed place on a cluster, and we have failures, we can understand, what was processed, what wasn't processed. And so, that requires a generalization of how you represent the steps in your code in a way that can be distributed and also restarted. So if you think of like word count, I've got to actually go through and identify each word and break up the line. If we're doing this in Java, right, we've got to actually identify what separates a word, spaces, and then we want to feed all of that into some kind of a variable, and we want to be able to then execute counts, based on how many times each individual word has happened. So with a directed acyclic graph, basically we can pull data from a source, tokenize it or break the words apart, and then start to accumulate this. This is a basic pattern that you have with a MapReduce. However, with the directed acyclic graph, it allows you to do this in a way which is going to allow it to be easily parallelized and distributed across many different threads. So, with each vertex or each step in this, we can actually have, queues that will distribute things between one step and the next, and then those can be distributed in parallel, and we can start to actually have more parallelization between all of these nodes. In this case, these are threads, but we take this step further and say we want these also to be distributed across a cluster. That's really where we start to get the ability to scale. And so tokenize, accumulate, combine, and suddenly we now have this architecture for distributing processing. So what's the difference between this and Spark? The difference is that the threads and how you manage or share work with Spark is actually using a cooperative work balancing technique that allows you to actually auto balance and distribute the work without having to have masters and workers, or to have a complex set of different components to the architecture. And that also means that when you're trying to see whether things are running or not, you don't need to have another component that says, okay, if this component's not running, that's the master, and if this component's not running, that's the worker, and what does that mean in terms of failover and keeping the whole system operational. With Jet, there is a much more elegant way of distributing work, where basically the nodes can look at the queue of work and pull work from the different nodes of the cluster, and it's like a self-balancing concept. So that's really the value of combining a distributed graph with the Jet platform. Why this is also useful is that if you're running this as a Java application, you want to be able to run a machine learning model, or you want to take data and pull it from a source, prepare it, and then feed it to the model. You want that to be done in some architecture that's also easy for applications to interact with, and not something that requires like dedicated hardware. This algorithm and approach that Jet uses actually is an embeddable approach, which means we can either run in a client-server model where jobs get published out to the cluster and run reliably, or we could also run in an embedded model where actually this is embedded inside of another Java application. So this gives you a lot of flexibility when you get into microservices types of architecture, and how you actually want to integrate this with your applications. So the other thing that is important about machine learning is that you've got to be able to prepare all of this real-time data and combine it with data that's also non-real-time, like data at rest from databases. You want to be able to do that in a way that can deal with looking at the data that is coming in real time in a time series manner, looking at slices or windows of data, and be able to do that in a way that can deal with things that might be out of sequence. If I've got a bunch of web clicks, if I have a series of credit card transactions, there's all kinds of sequential actions that are going to be analyzed to understand and create a real-time experience. Being able to look at windows of data and analyze the windows of data in real time with a continuous query is what stream processing is really good at, and that's really critical for being able to kind of sequence the data in a way that makes the data in context when you're going to feed it into an algorithm. Yeah, no, go ahead.
What's the problem here with sessions timeouts? What's the problem you described, the problem and solutions? What's the problem?
Oh, yeah, so when you're getting data from different sources, and that data may have different time series, you may need to standardize. Like, for example, some things, let's take IoT as an example. You might be sampling from some systems that provide 60 cycles per second, and others are 10 cycles per second. So you may have different, frequencies of when you're getting data, and you need to be able to normalize that to a common subset, and then the windowing constructs allow you to organize your time series data. That's also important in preparing data to ensure that things haven't arrived out of order. So for example, let's say securities trading, right? So, you know, if you're executing trades, but you've also got cancels and amendments to the trade, those, you know, it's important to understand, you know, the context of all of the different things within a certain window of time over which you're going to allow cancellation of a trade, you know, in order to basically process them all in the right sequence. So being able to resequence things requires that you can apply windowing constructs to that, and then sometimes you want overlapping windows, and sometimes you want tumbling windows, so that, you know, this window, there's no data in this window that overlaps with the next window. You know, telco analytics related to like analyzing channel changes and things from a set-top box, you know, that would be very time series oriented. That would require the sequencing of it in order to have context. And so that's one of the things that the windowing logic is very useful for. Does that kind of make sense?
What you just said about the context of the channel series. Say, for example, if you're using like video for communication wise between parties, like signaling and trying to get real time
Right.
response, how would you go about that instant
How would you deal with like video data?
in real time instant? Say, for example, like if you're doing a chat or you're doing a conference.
Yeah, so I mean, you know, any data that's flowing over the wire at some point has to be translated into an over the wire format, and then based on that format, you can determine how to analyze it, and it would depend on your use case. So the demo I'm going to do later is an image processing demo using the camera of the laptop. So you'll see a simple example of that, but it really would depend on, you know, I mean, if you're using like a chat application and you also have video to video, you know, most of the time video over IP, you know, it's going to have a digital representation, and then depending on that format is how you need to kind of think about it, and it also depends on what you're trying to analyze related to that.
Broadcast levels, haven't you?
Say that again?
If I said broadcast levels, just IP, just like on TV service, say, for example.
Yeah, I mean, you know, so there's different, you know, video standards, you know, that I'm not really an expert on all of the different video protocols, so I can't say like which ones there are, but basically, you know, at the end of the day, you know, you can look at the video format and figure out how to extrapolate images from video based on whatever that standard is. And, you know, if you were going from a raw source that's analog, you might actually have a signal processor that sits in between, you know, to convert it to a digital format. But that's all kind of more on the hardware side of things. Once it's into software, right, then, you know, it's just understanding that format and then what does that mean digitally and how you process it. Usually there's APIs that can deal with the lower level, like video processing, and what we would do is basically say, okay, we're getting digital video over a socket interface, or we're getting digital video over, you know, it could be coming, you know, could be chopped up and put over, you know, different protocols. So, you know, you'd have to really understand the specific use case to dig into that. But at the end of the day, if you can get a chunk of data and look at it in real time, now we know the video. What else do we know about it? You know, we need the metadata for the video, right? So the advantage of this platform is that we're able to take related streams of data or contextual data and bring them together so that our algorithms have context and meaning, so that we can say this is a football video stream, or this is a video stream related to, you know, two people chatting, and or Is the chatting related to the fact that they're on a, having a business meeting? Or is the chatting relating to the fact that they're also in another window playing some video game? I don't play video games, so I can't think of a good example of them, but like, I don't know, I have friends who play World of Warcraft and they get the headsets on and they're all on at the same time. There's a lot of different sources of data that are going on in real time that you could be analyzing: audio, video, and then the game data. And so, all of that would matter if you could be able to sequence it, and if you could be able to deal with like unordered and late data. And then, the basic thing that stream processing engines are good at is being able to enrich data. So you can pull data from something like Kafka, or from Twitter, or from a lot of sources, and then I need to know more about it. All right, I've got aircraft data coming in from telemetry from an aircraft monitoring system. Well, I don't know what type of aircraft that is. I know maybe the code for the aircraft that's tracked by the each aircraft has a unique identifier. There's also a flight number that's unique, and so those are raw tags that need to be enriched to give context, and that's really where stream processing adds value and prepares the data for machine learning. Being able to look up and transform the data into different formats. So you may get something that's coming from Twitter. You might need to group that data together. You might need to also transform data from a text into a number, and be able to then do mathematics and calculations on it. Because this is all in Java, Java is a very powerful language for working with data and manipulating data. Because it's sitting on top of a data grid, the whole platform is designed around being able to pull data, manipulate it, and present it. So you have very rich APIs that are at your fingertips. So the next thing that you have to solve for is the ability to have reliable execution of your machine learning. And this is where you want to be able to have things like exactly once execution if it's related to transactions, for example. You might want to have just fast execution because you're analyzing just web interaction for a video game, and you're trying to somehow personalize the experience or something like that, or trigger something. And then you might have at least once execution for something kind of in the middle, like it's a shopping cart and we see that the state has changed and we want to trigger an action and make sure that it happens. But if we accidentally have the UI present the same offer twice, it's basically they can only click on it once. So there's different patterns for how do you guarantee the execution of the steps of your directed acyclic graph, or the end-to-end transaction that you're trying to automate, including the step that is where you're calling a machine learning algorithm. And because you're distributing the algorithm onto different nodes, right? The possibility of failure, as well as the need to scale and do so reliably, that requires that you have some ability to save state and to understand, what was executed, what wasn't, and then to restart it for every individual parallel thread that is processing the same job, because you're distributing the job as opposed to just running one big job. So that ability to have distributed state snapshots, resilience, and do so in a simple way is kind of what the DAG brings, but also building that on top of a data grid. The reason for that is if you're not going to persist it on a data grid, then you have to have some other shared state. In Spark, you have something called a data frame, which is based on a lower level API called the resilient distributed data set, again, this is the same concept of a distributed copy of something. However, that resilient distributed data set is decoupled from other state persistence that's related to your processing. So for example, you're pulling data from Cassandra or from HDFS or some other NoSQL database, or you could be pulling, from Kafka. Having that, state persistence that is disk-based and not closely integrated with the stream processing engine means that the stream processing engine has, less visibility of where the data is. And it also means that the data has to be retrieved either from disk or maybe even from disk and over a network. And that all adds overhead to the processing time. And overhead to the processing time means that when you're trying to distribute and scale and be elastic, you're adding complexity to the overall architecture. So that leads to job elasticity. So being able to distribute your job on a cluster is a fundamental capability of Spark or Jet or other engines. But when you do this with Jet, it's actually very powerful, because if you add capacity, the auto work balancing of the workload across threads and across nodes means that the new node will basically go to the cluster and say, what work can I do? And bring it over and start executing work without disrupting the other nodes that are already doing work. It'll say, okay, give me some of the work that you have backed up, but it's not going to basically require a separate distribution mechanism to say, oh, here, take some work. So, that approach just makes it a more naturally resilient and elastic technique for processing. That also means that when you get rid of a node, again, the whole system can recover very well. And because then the state was stored in a data grid, that means that the recovery also doesn't require reading anything off of disk. And so those things make it very easy to maintain high availability and to have high guarantees on what gets processed and what doesn't. So we have these three basic processing guarantees. That was actually covered in another slide. I thought I'd pulled that out. So the other thing that is nice about this product is that it has a very nice built-in management tool that can show you exactly what's been executed and where it's been executed, which is useful both when you're creating your application, but also when you're troubleshooting it. And you can see, okay, which steps of my directed acyclic graph have been executed, how often, and then if I want to distribute this on a larger cluster, how well does it distribute? Because some logic is very easy to parallelize, such as transforming data, right? If I say I have, a string and I want to turn it into an integer or a floating point value, that's something that for each individual set of data that's going in parallel, you can do without knowing, all you have to know is, was this piece of data processed or not? So that makes it very easy to parallelize. And this management center really helps you actually diagnose that, and you can see, okay, look, these steps are, executing, but eventually we're trying to aggregate here because we want to display it on a dashboard. Well, because we're pulling a lot of different sources back together, then there may be less parallelization at some of these different steps. And by drilling into this, you can start to see some of those informations. So the next thing is, we need to be able to apply security to this. So this is another aspect that is good, really critical with the microservices or integrating with web applications is you have to be able to integrate with the application security model. Your web application has a completely different approach to security compared to what you have in an analytics platform like Spark and Hadoop and things like that. That's all based on, can you access data or not access data, not can you execute a transaction, or like who are you as a user, an individual user of an application, right? Using data that is in a dashboard is, that kind of access pattern is very different from, authenticating in the world of, mobile apps or web apps and things like that. And so, we integrate very well with the security model of Java, and we can provide process level security, and then we can actually apply more granular security to individual transactional logic and integrate that with your broader Java context. And it's all based on Jazz, which is a standard approach to security that Java has. And of course, Jazz integrates very well with things like LDAP and other authentications. And so this makes this a very easy way to integrate the stream processing as well as then the machine learning model that you plug into that into the suite. And we can also apply that security to job submission as well. So there's the actual identification of the security related to execution, but there's also the security related to, am I allowed to change a job and submit it and run it on a cluster? And that's another layer of security that's important because we don't necessarily want random people to publish jobs out to a real-time cluster and then have that cause, a huge amount of workload that isn't authorized and is, so it's one thing when you have like a Spark cluster that people are running batch ad hoc analytics on. If you're running a cluster that is supporting a actual real-time application, whether that's securities trading, whether that is, a web app or anything else, that architecture, can't be impacted by the fact that someone decided to create this crazy query and this complex machine learning algorithm and a bunch of other logic that suddenly generates this huge load computationally. So that's another aspect of security to keep in mind in this type of architecture. So we did talk about lossless recovery. One of the things that is also important when it comes to lossless recovery is what happens when you need to do maintenance on your applications. Being able to restart and upgrade and change the application is critical, and you can't have downtime. So, if I have a Spark cluster, I'm doing batch, I might just, bring the cluster down and say, nobody can use the Spark cluster on, Friday after midnight, and it'll be back, after 2 a.m. or whatever. With web applications and any other type of real-time computing, typically there are very minimal or zero downtime requirements. And because this is, again, built on that data grid architecture, that means, we're used to having 5-9 uptime multi-data center architectures and being able to do things like upgrade and deploy code without bringing down the cluster. And so that's another advantage that Jet brings. And, so sometimes you do have to pause the job while you're changing the cluster. And then you may have to deal with the fact that, the data didn't stop, right? So being able to actually, rewind and start processing, and restore the snapshot of the current state of data that's in motion, that's also a complicated thing that really would be challenging to do with an architecture as complicated as Spark and or some of the other solutions out there because they're not built for that kind of real-time world. We also allow the rolling upgrade of jobs. So that means like, I've got a job, I've got a machine learning algorithm, it's working, and then I decide, hey, I've figured out a tweak to it. My data scientists have come up with a new algorithm that's a little bit better. I want to be able to, deploy that. So I want to upgrade that job, and I can do that in a rolling basis where each node, I deploy it on one, and then it'll eventually roll around and upgrade the job on all the different nodes of the cluster in a seamless way, and with minimal increase in latency during that processing time. I talked briefly about this, but one of the advantages of Jet is that this is like maybe a 12 megabyte or something jar file. And it can be deployed in a client-server architecture. It could also be deployed embedded inside of a Java application. So you could have microservice or a Spring or JBoss or whatever your Tomcat application that you're going to want to be able to kind of also add stream processing into. We can support that embedded mode. And we can also have separation of the data grid and the Jet cluster, or they can also be running in an integrated approach. Yes.
Just a question about the previous slide. So it means you can deploy to existing infrastructure microservices managed by company, or you can provide your solution to manage all the application paths you deployables.
It could be, are you asking whether we offer managed services, or what are you, I'm not sure.
I mean, difference between embedded and client server.
Yeah.
Embedded, you can reuse existing infrastructure like microservices how they deploy.
Yeah.
Deploy your things there, or you can provide a solution where you say you control everything infrastructure.
Yeah, so basically you could have you have an application, it's already in production, and you want to enhance that application with these APIs. You could just add a jar file you add one line to your build to bring Jet in, and now you have that additional capability. There's a configuration file that determines like ports and how it operates and communicates. And your application now has all these other things. The advantage of that is not necessarily just that it's avoiding additional infrastructure, but it's also, you can see here, there's no network hop between your application and the stream processing capability. So if you eliminate a network hop, again, you're reducing latency. So that's another advantage of it. And then, because you're scaling your application and you're scaling your stream processing, sometimes it could be easier to scale them together, depending on your processing pattern. In other cases, it's probably better to separate the application logic and the stream processing logic. And that could be very use case specific. Another advantage of this is, in some cases, you may want to deploy into different environments like cloud or a fog architecture. And so, we actually have a customer that has deployed Jet clusters that can run on a truck, and that truck can actually be driven out to connect wirelessly to remote infrastructure for monitoring of like oil infrastructure. And so, the truck has that ability to communicate with the local network, and then it also has the wireless capability to feed that into a central cluster. And so, that's another advantage of Jet, is that it can run in a lot of different types of deployments because it doesn't require a big footprint. But it definitely runs in like cloud and all. It's just Java, so it runs on Kubernetes. It can run, just the bare OS or a lot of different deployment models.
So the embedded model actually, how does that compare with the Kafka streams?
So I believe Kafka streams does have does work like an API, but typically Kafka Streams still has your Kafka messaging, right? So Kafka Streams might be running embedded, but then the Kafka messaging, is typically running separately, and that's a Kafka cluster with dedicated disk, and of course, also when I'm saving state to Kafka, I'm writing to a disk, and then I'm also wanting high availability, so I'm writing to a second disk. So we're going to save to memory and then make another copy in memory on a different computer, and Kafka is going to make state sharing that's tied to disk. They do so very efficiently, but there is a little bit more complexity to their approach.
So there is a notion of state sharing with the embedded architecture, right?
Yeah, the embedded architectures are still, under the covers, there is logic running the JET, processing, and then the workload is distributed using JET. JET, there are network connections between the nodes of the cluster that relate to JET and IMDG, and then there's whatever other connections that might be related to the Java app. So there might be more, there'll be more network ports opened because you're running embedded, and you'll have more memory usage and different processing patterns because the JET processing is doing a different thing than the Java application. So, it really depends on your use case, which one is, the right answer. But it does give you flexibility because, that architecture, if it's running embedded, it's still using its own independent resources. The other thing that's an advantage of IMDG is it has off-heap data processing and storage, so that the state data or any other reference data and contextual data that you need to store, we will store that off of the Java heap. And so anybody who's like a Java person knows that Java garbage collection is the enemy of low latency or of even just consistent latency. You might have very fast, low latency Java application until a garbage collection cycle hits, and then all of a sudden your app is slow until that's done. And then that also doesn't efficiently use your processors, which means that, again, when you're trying to scale and be elastic and guarantee service levels, it just makes that all more complex. So by moving all of that off heap, that's another advantage of our platform. So I'm not going to spend too much time on the differentiators. I think I've highlighted a lot of them. Overall, I would say it's just simpler than Spark. It's really a Java-friendly approach, and Spark is something that Java developers find kind of intimidating, and the operations teams find difficult. On the other hand, Spark's great for batch and doing very large amounts of data. Well, I'll just basically explain this. So this is it's a fairly simple demo. It's pulling the webcam video, and then it's really just looking at using an image classifier, and then it gets the output of that, and it looks at the score, and starts to just display that result in a GUI. So it's not a very sophisticated DAG, as it will, but what you can see is there's a webcam source, so the pipeline is drawing directly from the webcam, the Java application talks to the webcam, and it's looking at feeding the data into the classifier, and then aggregating the output scores, and then we have the sync. The sync is basically just a simple program to take the output and take those images and display them in a Java panel. So there's not a ton of code in this example, but basically, it just illustrates, the value of being able to like call a Java classifier, a Java-based machine learning classifier, feed it data, and then take some action. So the real illustration here is that, being able to connect sources of data and then determine an action based on the output of a machine learning algorithm.
So does it do any feature engineering or just?
In this particular demo, we're not doing any feature engineering. We have another demo that shows some analysis of Twitter, and it does some preparation of the data. That one doesn't really, I wouldn't say it does feature engineering, but it does a little bit more preparation of the data before feeding it to an NLP processing. Essentially, if you think about this, this demo with the image processing, effectively this could be the feature engineering step actually, because it's just taking a raw feed and then it's classifying it. So that is a form of feature engineering really. It's just not doing that much after the feature engineering step. But it illustrates, I think, you do need to kind of have several steps in your machine learning. You need to have analyzing the data for features. Then you need to be able to like do some calculations, enrich that with other data, such as what is a horse, or like, am I analyzing, sentiment on a person's face, what's the context of that? If I do some classifying of sentiment off of a camera, I might be doing that in order to determine whether or not somebody is a happy or sad customer at a checkout counter, or I might be analyzing their face to determine whether they look nervous because they're in the TSA line. So context, combining the raw machine learning algorithm with contextual data is really the value of what stream processing brings to kind of the table. And it's a big difference between analyzing, thinking about whether someone's happy or sad in a retail environment or hospitality, like you're coming up to a counter of, the desk of a hotel versus, people who are, in public places, and you're trying to understand sentiment and then determine like whether or not that's somebody suspicious. And if you're in TSA line, actually, not only could you connect that sentiment with like some context, but that they just, passed through and authenticated themselves and their ticket information, so like where they're traveling from and to. So there's like a lot of contextual data that you could use in a transportation type of, a airport environment that would be very time relevant, And so time series analysis, and then being able to immediately connect that to actions, that would be another good example of one where you'd want to be able to combine these technologies.
Presumably you could also put in other information, like for example in a sort of a airport TSA line, you could figure in things like how busy the airport was in general, which would then affect people's moods because they're waiting for longer, so then that affects the sentiment. You can pull that in and correlate that.
Yeah, that's a good point. Understanding, like also just comparing, the data across, everybody that you're looking at, right? If everybody looks unhappy, then that person's just unhappy because everybody's kind of pissed off. And versus if there's one guy who looks kind of like nervous and everyone else seems pretty relaxed, then, that's an anomaly that would be easy to pick up if you had all of the data you needed in order to understand and identify that anomaly. So I guess that's kind of the main things I wanted to cover today. If you'd like to kind of get more in depth on what do the APIs look like and everything, we can show you some code, but probably the better thing would be for us to kind of, send you some, information, or you go to our website and, this is all open source technology. You can play around with it. You can find video tutorials and blogs and code samples. We've got, I don't know how many different, like 20 different, probably 30 different like code samples for Jet, plus, 6 or 8 demos that are on there. We've also got, for the other part of our product, IMDG, like 500 code samples available. So there's a ton of information that's available online, and we are also happy to kind of chat with you today, but also in the future, we will be planning some more events. And in fact, if you really want to get hands-on with this technology, we are getting ready to do our Jet 3.0 launch, and the best thing would be for you to take a look and sort of watch this space, because we'll be actually doing a whole series of hands-on half-day workshops where we'll actually walk through how to do stream processing in Java. And those tutorials, a lot of the concepts will be very applicable to many different frameworks, because the basic concepts are the same. Time windowing, dealing with pulling data from source, outputting the data, and kind of how do you join streams of data together? How do you join real-time data with non-real-time data for enrichment? All of these different concepts will be covered in the upcoming training sessions, and so would encourage any of you guys who are interested in getting more hands-on to keep an eye out for that.
Sorry, I have a question actually. So, is there any way to get rid of duplicates actually? Because the messaging platforms can do duplicates.
Mm-hmm.
Okay. I mean, you talked about at least once and process.
Sure.
What's the guarantee?
Yeah, there are techniques for getting rid of duplicates. It kind of depends a little bit on how do you identify duplicates. So when you talk about like identifying out of order processing or identifying duplicates, a lot of times you need to think about where's the source of the duplicate to kind of create the best solution. Certainly we have that ability to keep that data in memory, and so there are some capabilities in the APIs to kind of ensure that you're only picking up something once, whether or not that's coming off of, say, Kafka or coming off of WebSockets or different sources. That may vary how you are going to prevent or identify duplicates, right? If it's Kafka, you can always kind of go back and look and see, like, what the data is sitting on Kafka, and so there's ways to kind of build that logic, based on specifically looking at that. If you're getting that data pumped at you over, TCP/IP, you might have to store some of that data for a certain period of time. And so what you could do is, in your windowing logic, there's ways to kind of express, and also depends on, like, if it's got timestamps and or transaction IDs and other things, you can with your filtering and your window definition, you could define the query in a way that it would eliminate those duplicates. Yeah, because you're saying, okay, I'm looking at this window. Also, your windowing logic could be time-based, but it can also just be based on counts. I can say every 1,000 messages is one window, and I'm, having an exclusive tumbling window for every 1,000 messages. And, it also depends on whether your messages have a unique identifier in there that makes it really easy to identify duplicates, or if it's just like, video feed coming from a camera, then it could be quite tricky to identify duplicates. So.
We do stream processing using microservices,
Mm-hmm.
we need of Kinesis. whatever we do, right, when we try Kafka and then we try Kinesis, whatever we do, duplicates are there.
Hmm.
So for TCP timeout, because of even the publishers replies.
Yeah.
So the way the messaging streams are designed, like, you always see duplicates in the downstream.
Yeah, and so, understanding the source of the duplicates kind of, really is important to thinking about the way the logic you need to do to kind of remove them.